Okay, in this video, we are going to look at the synthesis of alkylamines for the most part. Okay, and just for review, we've already had in this course lots of reactions that make amines, so let's review those right now. Earlier part of this class, we saw how you could hydrolyze an amide group right here with either strong acid or strong base, and this will give you the free amine after you do the necessary pH adjustments. Okay, in addition to this amine synthesis, we've also had several reactions to date that introduce nitrogen into an organic compound where there previously was not a nitrogen. So let's look at some of those, and we've had these for a long time, some of them way back to the first half of the class. All right, so you can introduce nitrogen through an SN2 reaction. Remember, sodium azide will react with an alkyl halide or tosylate to give us the azide, and sodium cyanide will react with under very similar conditions with the same type of substrate to give us a nitrile or a cyanide. These are both examples of SN2 reactions. Everything you know about the SN2 reaction applies to this. It goes best with primary or methyl halides, and tosylates and iodides are the most reactive, more reactive than chlorines or bromines. Okay, in the aromatic chapter, we saw how you could introduce nitrogen through a nitration process, nitrating an aromatic ring using nitric acid, sulfuric acid gives you an organic nitro compound. In the ketone aldehyde chapter, we saw how that you could take a ketone and react it with an amine under mild acid or base, and if you use a primary amine or ammonia, you'll get an imine. And if you use a secondary amine, you will get an enamine. Okay, in the carboxylic acid derivatives chapters, we saw how you could make an amide from either an ester, an anhydride, or an acid chloride, or a carboxylic acid. Okay, earlier in this class, we also noticed that, or studied the chemistry of epoxides, and noticed that epoxides are useful in the SN2 reaction. So these top two reactions here, the halide reacting with sodium azide or sodium cyanide, could just as easily occur with an epoxide. Okay, so if this epoxide, cyclohexene oxide, were treated with sodium azide, then a pH adjustment, we would get the azide, and this is a nucleophilic epoxide ring opening, so it would go to produce the transalcohol azide. Okay, likewise with cyanide as a nucleophile, we produce the trans-hydroxynitrile derivative. Okay, so let's look at some reactions that make actual amines as the nitrogen-containing structure. First, let's look at the SN2 reaction. All right, we can do the SN2 reaction with ammonia. Okay, I don't have this perfectly lined up here, but ammonia is a nucleophile. It can do the SN2 like so, displace the halide. Most of the SN2 reactions you've seen to date have anionic nucleophiles. This has a neutral nucleophile, so the product is going to be cationic. So what you make here is the ammonium salt. Okay, and if you do a pH adjustment, if you want the free amine, you're going to have to adjust the pH to something higher than the pKa of your average ammonium salt, and we say we'll just treat it with sodium hydroxide, or sometimes we'll just use the word basify, which is like the term acidify we we're using in the carboxylic acid and aldol chapters. And this is going to produce now the free amine. Okay, this reaction has a little bit of a complication, and that's the fact, consider the point where the reaction up here at the top is halfway over. Okay, at that point, you'll have the starting material coexisting with the ammonium salt. Okay, so what we have is a situation where the pKa for ammonium ion and the ammonium salt are relatively similar numbers. So if these are coexisting at the same time, they'll do an exchange process, and once you generate this, it can now do an alkylation, and after basification, you would now produce the amine that has two R groups on it. So this is the problem. We call this problem over-alkylation. Okay? And it is occurring because the initially formed ammonium salt and the starting amine are in equilibrium with each other. Okay? The best way to do this is to use a very, very large excess of ammonia, which is a cheap compound, and you can do that. So if we treat benzyl bromide here with excess ammonia, we should get benzylamine after we adjust the pH so that we isolate the free amine and not the ammonium salt. Okay, so let's predict. Okay, sorry, we'll do some problems later. All right, there's also SN2-based methods that occur over a couple more steps, but they avoid this over-alkylation problem. So one is the Gabriel synthesis. This is where we're going to take potassium phthalate, shown here. And we're going to use this to do the nucleophilic addition. Okay. This can't really alkylate more than once. This is essentially a non-basic lone pair. Because of those two carbonyl groups, the resonance interaction with those two carbonyl groups. This is a imide, and like an amide, it can undergo a hydrolysis with KOH. Oftentimes it's preferred to use hydrazine here to release the amine. This is because hydrazine forms this stable cyclic product shown here. Okay, and this gives you the free amine. So we have no problems with over-alkylation. We can also use the azide-based route. Okay, you probably are wondering, what are azides good for? And they're good as precursors to primary amines. Okay, so the azide would do the SN2 reaction very well with this halide shown here to give you the allylic azide. And now you could treat this with lithium aluminum hydride. I had hydrogen and platinum and palladium there, but I don't think that'll work here. Okay, and this would give you the amine. Okay, probably you'd have a problem with hydrogenating the alkene group in this case. Okay, but hydrogen and palladium or catalytic hydrogenation conditions do reduce azides to amines. Okay, so lithium aluminum hydride or hydrogen or catalytic hydrogenation will do the reduction. We can also reduce nitro groups. So the product of nitration, nitrobenzene, could be treated with tin HCl or iron HCl as a reducing agent, and in many cases you can also get away with catalytic hydrogenation, and this will produce the free amine after you do the necessary pH adjustment. Okay, you might wonder, how do we convert benzene directly to aniline? So here's benzene, we can convert it directly to aniline by nitrating first. Okay, so step 1, this is kind of a little bit of an awkward presentation way it's set up here, but you'll see what it does. Step 1 would make that, and step 2 would do this. So this sequence of 1 nitration, 2 nitro group reduction is an excellent way to introduce a nitrogen onto a benzene ring. Okay, we can also reduce a nitrile. Okay, reaction of an alkyl halide and an SN2 reaction would give us a nitrile, and this would produce our product. Okay, right here. And I think we looked at the mechanism of this in the previous chapter. Note that the 2 hydrogens that you see here in magenta come from the reducing agent. All right, another important thing to note is that an extra carbon is incorporated. All right, so there's an extra carbon. Okay, so you gain a carbon when you make an amine this way. So this is different than the azide. So use the nitrile when you want to add a carbon. Use the azide when you want to keep the same number of carbons. Okay, when we reduce amides, what we do is we take the C double bond O and we convert it to a CH2 group. Okay, like you see there. This is a little bit different than the way other carboxylic acid derivatives react with lithium as aluminum hydride. What's depicted here is a tertiary amide, but all amides do this. So the only thing that happens when you reduce an amide is you get rid of the C double bond O and replace it with a CH2. This is the only reaction where we can't take this liberty and just call lithium aluminum hydride a source of H-. We will, in the first step here, we're going to get hydrogen adding to the carbonyl group. But we need to consider now that it's not really an O-, it's an aluminum salt. And this makes it a decent leaving group for the nitrogen lone pair. So the nitrogen lone pair is going to kick out the aluminate. We're going to get now an aminium salt, and another molecule of hydride equivalent is going to nucleophilically add to the aminium salt, and this is going to give us the product. Okay, let's do a few problems here. Let's complete each reaction. All right, so in the first one, we're nitrating a benzene ring and then reducing it. So we're going to get an NH2 group somewhere on this benzene ring. All right, so what do we have to do here? We have to figure out who's the best electron donating group. So this is the stronger EWG. I used the term boss group when I was teaching electrophilic aromatic substitution. So we're wanting to go orthopara to this. All right, so there's para to that. We can't go ortho. All the orthos already have something there, right? So this is where we're going to see our amine group end up, and that is the predicted product. Okay, lithium aluminum hydride is going to react with this amide. And lithium aluminum hydride will not react with carbon-carbon double bonds usually. So what we're going to see is we're going to take the C double bond O and we're going to reduce it to the corresponding CH2 group, right? So here's our product. Okay. And remember that those 2 hydrogens came from lithium aluminum hydride. All right, this epoxide, we're going to treat it with a large excess of ammonia. This means it's going to do the SN2 reaction. Alternatively, we're going to treat it with sodium azide followed by lithium aluminum hydride. This is also an SN2. Okay, both of these are equivalent ways for converting a leaving group into an NH2 group, or for displacing a leaving group and producing a primary amine. Notice that nothing is going to happen to this carbon. All right, so we should not change the configuration there, but the SN2 goes with inversion of configuration, but it's not going to matter here because it's going to go there, and that's a CH2 group, so we don't have a choice of stereochemistry there. It's only one isomer possible, and this is our product. Okay, we should form the CO bond. The configuration should match the configuration right there. If you want to have a little fun, you can go ahead and assign the R and S configuration on your own, but I'm not going to do that. Okay, and the last one, we're reacting something with sodium cyanide and then reducing the product. Okay, and remember that with sodium cyanide, not only do you introduce the NH2 group, you also introduce a carbon. So we're going to be introducing both of these atoms. Okay, so what do we need as a precursor? We're going to need something that has all of these atoms in it, and there should be a halogen at the point of attachment. All right, so this is what we need for this molecule. X could be chlorine, bromine, iodine, or tosylate. Whichever one would be best would depend on which one could be made more effectively. Had this been a multi-step synthesis problem where you had to make the compound I just showed in blue there, then that would be a consideration. Okay, let's look at a slicker way to make amines, and this is called reductive amination. Okay, recall that if you treat a ketone with ammonia, you'll get an amine, you could get an NH2 plus, okay, as an intermediate in that process. Either of these, or I believe the aminium salt is the one that's more easily reduced here. But if you take this and treat it with a reducing agent like hydrogen and platinum, sodium borohydride. In this case, I have sodium cyanoborohydride, but sodium borohydride would work for this step all by itself. What you'll do is you'll convert the C double bond O to the corresponding amine. You'll also have an extra hydrogen that was originally at the carbonyl group, carbon. Okay, what's really slick about this reaction is that you can do it all at once. Okay, so if you take ammonia and sodium cyanoborohydride, it only reduces the aminium salt. If you used sodium borohydride in the one-step reaction, you might have a problem. It's very likely that you would produce a lot of this as an unwanted byproduct, right? Because sodium borohydride, we know, is reactive to ketones, okay? So sodium cyanoborohydride has reduced reactivity relative to sodium borohydride, and it's too weak to reduce the C double bond O group. So you often see that used selectively in this process. Okay, are used as the reducing agent in this process because it's very selective. Hydrogen platinum is also more reactive to the carbon-nitrogen double bond than it is to the carbon-oxygen double bond, so you see that used frequently as well in reductive amination. All right, it's a very general process. I showed it with ammonia up here. Well, you can use a primary amine or a secondary amine. All right, so this ketone reacting with this primary amine here, this ketone, this primary amine, reacts with in the presence of sodium borohydride to produce the amine here. The new bond that you made is that one. Okay? All right. The secondary amine is now going to react to produce here this product. In this case, there's no question as to whether it's the aminium salt reacting, because there's no sodium cyanoborohydride. Okay, this would make the enamine, right? Okay, so and the enamine, of course, forms from the aminium salt. All right, so this one can only form by reduction of the aminium salt. Okay, all right, so no ambiguity as to what's being reduced in the case of using secondary amines, because the enamine is not likely reactive to the sodium cyanoborohydride. All right, so we're going to do a couple of problems here. Now we're going to show aldehyde ketone combinations that can be employed for the synthesis of each amine. If it's a tertiary amine, there's going to be 3 combinations of aldehydes and amines, or ketones and amines. If it's a secondary amine, there's only going to be 2. Okay? All right, so let's look at each one individually. All right, so we could form either bond A, bond B, or bond C in this reaction. Okay? And let's just look at each one of them. All right, so if we form bond A, we're going to need a 4-carbon aldehyde with a double bond in it, and we're going to need an amine that has the rest of the molecule intact. So this is the combination of aldehyde and amine that you would need to make that compound by reductive amination. But you still have 2 other choices. What about B? Okay, if we want to make bond C, bond B, we're going to need cyclohexanone as our carbonyl additive, and we're going to need molecule that basically has everything to the right of the B slash, everything to the left of the B slash in it, and this would involve the amine shown here. Okay, and disconnection C would involve the aldehyde, acetaldehyde, a 2-carbon aldehyde, and then everything above the slash mark by the C is required in the nitrogen component in this process. Okay, which of these is best? What you would do is you would go find yourself a chemistry catalog, find out which of these is the cheapest, and that's the one that you would use. Okay, all of these are equally good. They may produce the product with different efficiencies or whatever, but in theory, all of these are just as good. I'm going to say the top one's not as good because we might isomerize the double bond into conjugation, but the rest of them are probably all just as good. Okay, this one. It's a secondary amine, so we're only going to have 2 combinations. Okay, A requires cyclohexanone, and then the nitrogen that contains basically everything to the right of the slash mark for A. Okay, so it requires cyclohexanone and methylamine. B requires a 1-carbon carbonyl group, and that's formaldehyde, shown here. And then it requires everything to the left of that slash mark, okay, for B, as the nitrogen containing component. So cyclohexylamine and formaldehyde condense in the presence of a reducing agent to produce the compound shown there. Okay, let's now begin looking at reactions of amines, and this is, I'm going to stop the video here. This is what's going to start with the next video. Okay.